between eating a meal and running a mile? You could say that a meal gives you energy, while running uses up that energy. A chemical reaction is going to be described in the same way. Some reactions release energy and other reactions absorb energy. Let's review exothermic reaction. We discovered this word at the beginning of the year, but we're going to bring it up again as we finish our chemistry unit. And basically, a chemical reaction that's exothermic is a reaction where energy is going to be released. Now, we talked about exo meaning to go out or to exit. Thermic means heat energy. So these reactions are going to give off energy. So let me write an example. An example that you can put in your notes is going to be like sodium, pure sodium, which we know is highly reactive to water. If we mix that with chlorine gas, so we put a little 2 there because it's diatomic, we know that we're going to get sodium chloride, but this is an exothermic reaction, so you'll see chemists sometimes write plus energy. Go ahead and balance this chemical equation, put a 2 in front of there and a 2 in front of there, and you have a balanced equation. This is an exothermic reaction because this reaction gives off energy. If you break a light stick, that's going to be exothermic. Electrical energy, when you put batteries into a flashlight, that's an exothermic reaction. If you have like a campfire, that's also an exothermic reaction. An endothermic reaction, if you recall, is going to be a reaction where energy is taken in. Endo, recall, means to go in, so absorb, inside. The energy that is taken in during the endothermic reaction is often written as a reactant in the chemical equation. So let me give you an example. So energy is going to be on the reactant side this time. For instance, if I have water, and we talked about this in class, if I add energy in the form of maybe electrical energy, I'm going to break down this water molecule into its 2 components. And these are diatomic, so I need to put a little 2. And then I need a balance. So I'll put a 2 here and a 2 here. Notice that energy is on the reactant side, while the other one, energy, was on the product side. And that has to do with being exothermic or endothermic. All right, we need to talk about the law of conservation of energy. We talked about the law of conservation of mass when we balanced equations, and we realized that if you start with a hydrogen atom, you need to end with a hydrogen atom, but it could be in a different combination. Law of conservation of energy is kind of similar, where energy cannot be created or destroyed in a chemical reaction. Also, energy can change forms, so it can look differently. And also it can be transferred from one object to another, kind of like, passing off a baton in a race. Like if you ever watch the Olympics, how the runners pass a baton. So if we apply this law of conservation to our exothermic reaction, energy is released in the exothermic reaction because it was first stored in the chemical bonds, in the reactants. And energy taken in during an endothermic reaction, where it's absorbed, is stored in the products. So that energy is just recycled, it's just transferred. Okay, now we're going to go into what's called the rates of reaction. So the speed at which a new particle is formed is called the rate of reaction, so the speed of the reaction. We need what's called activation energy. And activation energy is going to be the smallest amount of energy that the molecules need to react. For example, if you have like a bowling ball and you can roll it down the alley, the bowler must first put some energy in to start the ball rolling. Chemical reaction is the same. You need to give it like a kick start, like a kick in the pants, I always say. Another example of activation energy is like striking a match. Before the match can be used to light a campfire, the match has to be lit. So you have to like interact the chemicals together. We do that all the time in this lab. When you guys did your single displacement reaction last week, you had hydrochloric acid and you had to introduce the metal to the hydrochloric acid in order for the reaction to start. So you needed to give it that activation, that kick in the pants. Sources of activation energy could be friction is one source. You can have an electrical spark, like in a car's engine, and that begins burning the gasoline. You could also have like light that causes activation, and that would be like maybe photosynthesis. The sunlight triggers the reaction. And so we're going to look at a graph a little bit later, and we're going to include that activation energy. But let's talk about factors that are going to affect this speed of reaction, this rate of reaction. The first one's temperature. We discussed this at the beginning of the year. If you increase the temperature, that will make the particles vibrate faster. They're going to collide a little bit more. We're going to have reactions starting. We're going to have chemical bonds being made. Concentration's also going to affect the rate of reaction. If we have a dissolved solution where we have more water and less solute, the reaction might be slower. But if we increase that solute, the concentration is going to affect rate of reaction. Surface area also affects rate of reaction. We did a demonstration back in the fall where we had Hershey Kisses. We put them in our mouths, and the first time we didn't move our tongues at all. The second time, we did move our tongues, and the third time we chewed it. And the third time is when, that rate of reaction, the saliva broke down the chocolate and we were able to eat it quickly. So surface area makes a difference. If you take your fist and you pretend that that is like a crystal or a particle, if you put that in solution, it's just going to take longer for the chemicals to react. But as soon as you break it apart into smaller particles, the solvent or the chemicals that you're reacting it with can interact a lot quicker if you break it apart. We did, when we did our single displacement reaction, when we used powders, we noticed that they reacted a lot quicker. But we had an aluminum pellet, and I kept telling you, like, that pellet is going to take longer to react because it's in that solid pellet form. But if I had aluminum that was all broken down into particles, just smaller particulates, it would react a lot quicker. A new word that you might not be familiar with is an inhibitor. An inhibitor is going to affect the rate of reaction because it's going to slow it down. It inhibits, slows down the rate of reaction. For instance, preservatives are going to slow down food from spoiling. And antibiotics sometimes are inhibitors. Like penicillin prevents certain kinds of bacteria from making a cell wall, so that bacteria will die. So an inhibitor slows down or stops a chemical reaction. Catalysts speed up reactions. They're going to lower that activation energy, that kickstart. They're going to lower it, and they're going to make the reaction happen a lot sooner. Enzymes are examples of catalysts, and they speed up reactions in your body. So these 5 factors are going to affect the rate of reaction.